So, brought my attention that I might have brushed over the last bit of the last lecture, so I want to just go over that last calculation that we did, which will kind of lead us to an example that I want to do, which is calculate. So try and take some of the formal things that we've been doing and actually do an example. You're going to be doing more examples in your exercise sheets, but I'm going to do it easy. It's not just an easy one, it's an instructive example because we're going to be focusing on a scalar field grid that has great use to us because it is an example of a formal field theory. What we call the Wilson-Fisher, condensed matter theory is called the Wilson-Fisher fixed point. You might know it as capacitors bipolar theory. But this is an interesting and sort of example because it occurs in many places in condensed matter. In particular, we said that these formal field theories play a role in phase transitions. Well, the Wilson-Fisher scalar is one such theory that plays a role in phase transitions. It's quite important to statistical mechanics as well. One way, but it's getting there. Last time, I want to remind you that we were asking what kind of constraints should we have on the energy momentum tensor that we calculate. We found that yes, the energy momentum tensor is if the energy momentum tensor is symmetric, it means something. If it's what we're going to show now is if it's straight free, it means something, etc. So these are the constraints that are required of the energy momentum tensor, and I'm going to outline, if you're an energy momentum tensor, what would you look for in an energy momentum tensor? Okay. So by way of here, the last lecture, I said that if x mu transforms to x mu plus some psi mu generates a conformal transformation. Then this vector parameter that parameterizes this transformation must be a Ken vector. Not just any Ken vector, it must be a conformal Ken vector. Conformal Ken vector tells me that it satisfies the conformal Killing equation. Says that d mu psi mu plus d mu psi mu is 2 over the number of dimensions of space that we're working in, multiplied by the scalar product of the differential operator with this vector. And typically use that pass for the indices. Okay. Given an anti-momentum tensor that we get associated to this transformation, usual nuclear story, we can use this to construct some current, A nu, labeled by this sign. This is not an index; it's a label. This is what I get if I can take T nu, subtract it with psi nu. Then my claim was that this guy is conserved. In other words, it's divergence free. Another condition on the energy momentum tensor holds. That's one set of condition. So this is the divergence of dv nu and nu, where the product rule is just dv nu times sin nu plus t nu times nu. This is vanished because energy momentum, the canonical energy momentum tensor is conserved. So it's necessarily zero. And then this guy, I'm going to add two of them, so I divide by two. Off of t nu nu so nu plus t nu nu so nu. Then these are repeated indices, so I'll change nu to nu and mu to mu, and then I'm going to use the fact that this is symmetric to exchange this back and then pull out this factor of mu. That was the manipulation that I skipped rather quickly last time. Assuming that everybody's familiar with these kinds of tricks that we play. And then the thing in brackets is the evidence that this replace that by eta by two cancels of that half, so 1 over d dot psi, and then eta mu times t mu. And eta mu contracted with t mu just pulls out a trace of this rank 2 tensor. This is what we would normally call t mu, which is the trace of t mu. T mu has a matrix representation. What I'm doing here is counting the elements of the diagram. And if this is to be a conserved current, then I require this to be 0. And this is 0 if the thing in brackets vanishes or this thing vanishes. The thing in brackets vanishing means that the whole thing is trivial. There's no transformation. So that can only mean that the energy momentum tensor has no trace. So if I have a formal field theory, then the one that is invariant in a formal transformation like this, then the energy momentum tensor must be traceable. This is an important constraint that we will impose in formal field theories, and we will see that one of the really important things that's going to show up shortly is the idea of formal anomalies. In other words, I start from the classical formally invariant theory, and when I quantize the theory, something goes wrong, and I pick up an anomaly that breaks a formal invariance. How it will break a formal invariance is that this thing will no longer be 0 on the right hand side. Okay. Not only that, the structure of anomalies is well constrained in a quantum theory. So it's not just any old right hand side that will get, it's a very specific form of the right hand side that will get. And that form, the right hand side, will dictate for us a lot of the internal structure of these conformal field theories. And if I'm telling you that these conformal field theories show up in things like phase transitions, then it's worth paying attention to the internal structure of these theories, which is why we take them all these so seriously. Okay, great. So now I want to do an example that's based on all of this. And the example that I want to use is the following. Let's calculate the energy momentum tensor for a particular theory. I want to consider the mass of this scalar field theory defined by the following action. Action is a functional of the scalar field phi. This is the integral over space-time d for x of half d mu phi, the usual magnetic term, minus lambda over factorial. So here, oh no, I'm just so if you're familiar with Pascal's field theory, this is something that you can see a lot. In fact, if you guess Cameron and is another one in the past, I've done this course in previous iteration before when we were using potential methods to quantize things. This is kind of the canonical quantum theory that you would consider, because it's got this phi to the fourth term, and the phi to the fourth term is a perturbation on a Gaussian theory. The Gaussian theory would have a phi squared, so that would be a mass surface theory. And the reason why you consider Gaussian theory is because everybody gives you Gaussian integrals. And then what you do is you consider this phi to the fourth perturbation on the Gaussian integral, and that kind of leads you down the rabbit hole to final diagrams. Okay, so where's the phi squared term from? Well, the phi squared term has been two, so one way you can think of getting this theory is to actually add a term that looks like a minus m squared phi squared piece, right? So that's your Gaussian contribution. And then you say, well, I've got two parameters in this theory, lambda and mass, right? And I'll tune the theory. There's some constraints on what I mean by tuning the theory, but I tune the theory, I tune these parameters so that I go to the limit where the mass goes to zero. Okay. So in that limit, this theory becomes a conformal field theory. That's really what I want to focus on. Now, then we'll return back to this example a couple of times down the line, where we'll extract its conformal properties a little bit. The point here is that this defines a conformal field theory. This called the Wilson-Fisher That's statically but formally invariant. Quantum correction will break this when we get to that point. Okay, it's going to be an important point. Get there. But for now, let's just focus on classical theory. So if I'm claiming that this theory is a classical formal field theory, then I would expect that the constraints that we came up with the energy momentum tensor must follow, namely that it must be symmetric and it must be trace free. Okay. So we would expect that the energy momentum tensor that we calculate from this action must be symmetric and trace free. So let's check that. So the first thing is we need to calculate the equations of motion. This would be enough to do. The Lagrangian density associated to this action, we can make it sitting inside of this here, for L. Calculate the L by phi. So one term that involves phi, that's the stack, so that's minus lambda over p factorial by cubed. Factor of 4 takes out a factor of 4 in the denominator. Similarly, the L by derivative dv phi is one term that involves the derivative, and the product rule for differentiation tells me I'm going to count for this thing twice. This is just dv phi. And then I have an expression for what the energy momentum tensor must look like. Sorry, before I get there. Which means that the equation of the motion is the derivative of this guy. So derivation, we need dv phi plus lambda over 3 factorial pi cubed. Okay. So now I have an expression for the canonical energy momentum tensor that this theorem generates for us. T is d phi mu phi minus eta mu times the Lagrangian. Okay. I don't need to substitute back into this to see what it is. I'm just interested in the properties. Okay. In particular, I want to make sure the properties that came out of this whole. So properties of this energy momentum tensor are as follows. First thing is this is clearly symmetric, right? If I exchange mu and mu, yes. So T mu is same as T mu. So symmetry is preserved. Second point we should check is that it's a preserved energy momentum tensor. It means if I differentiate this guy with respect to mu, x mu, then I get 0. So let's check that. This is d mu of d mu phi, d mu phi minus eta mu mu. And the Lagrangian density is d mu phi mu phi plus d mu phi mu phi minus eta mu d mu times the Lagrangian. This guy acts on this index, brings it down and replaces it by mu. That's d mu times the Lagrangian. And now I can substitute it for the Lagrangian density. What I will find is that this is d mu phi plus lambda factorial by cubed, all multiplying this d mu phi. This is the Euler Lagrange equations. The thing in brackets vanishes. This is 0. Okay, so indeed, the canonical energy momentum tensor that we calculated is a conserved energy momentum tensor. So far, so good. So what about the trace? The third property that we're interested in is T mu mu. Remember, some repeated repeated indices have to obey the Einstein summation, which said that I have sum of these, right? Effectively, what that means is that this is just eta mu mu T mu mu a function of those two. And if I plug in for T mu, then this is just d mu phi d mu phi minus 4 for the Lagrangian density, because I'll have an eta mu here, one upstairs, one downstairs, and that's just the Kronecker delta. The delta mu is 1 plus 1 plus 1 plus 1. That's 4, that's why that factor 4 is. Now, if I substitute it in the Lagrangian density, I will find that this is equal to using the equivalent quadrant minus d mu phi minus phi d mu. Whatever this thing is, it's just non-zero. Okay, so to recap, I said that if I have a formally invariant theory, then its energy momentum tensor is trace-free. Now I claim that Wilson-Fisher is a formally invariant. I can check this in formal transformation, so the formal transformation will come out, leave the action invariant. But this is not trace-free. Okay. Is there a contradiction? Well, no, actually, that's not a contradiction, because I know the canonical energy momentum tensor is not necessarily the one we want. And there's the freedom to improve canonical energy momentum tensor by something that will make it trace-free. I showed you an example in the last lecture in gravity, for example. Canonical energy momentum tensor generated by Hilbert's theorem does not even couple properly to gravity. So we proved it. I said the improvement there is called Bell-Fontaine. So we can do something similar here as well. And here we have an idea of what it is we want. We want something that's going to account for these terms. Something that's going to make these two terms vanish. So Now we can add to the energy momentum tensor this improvement term. I'll call T nu movement. And this guy is going to be 1/6 of eta nu d, let's say lambda, d lambda of phi squared minus d nu again acting on phi squared. My claim is that term takes care of this problem with the canonical energy momentum tensor makes it trace. Let's see why that is the case. So firstly, anything that we add to the energy momentum tensor mustn't break these properties. We've already established that these are the things that we want on the side, and it better keep those, right? So we should first check that this is not symmetric. Sorry, this is symmetric, and indeed it is. This is symmetric, this is symmetric. Adding these two things together means that this truth version also symmetric. So the improvement in U is the same as in U. Right. Secondly, check explicitly that you take the derivative of the side with respect to mu, say, then you'll get a d mu d lambda term here, and you'll get a d mu d mu term here, and because it's a dummy variable, that this guy t mu mu also vanishes. So okay, that doesn't break that property. And that means that all we need to check the trace of this thing. So if I multiply it by eta mu nu, we'll find that eta mu nu t mu movement is 1/6 of eta mu nu is going to give me 4. Yeah. Like this. Eta mu, when I have eta mu d lambda of phi squared minus d nu of squared. So this is going to give me 4 d lambda of phi squared. Yeah. And then this is going to act on something that is need to bring it down. Let's pick nu. So this is going to give me d nu, same as the d lambda, so that's minus one of those guys. Squared. So that's 3 divided by 6. It's half d lambda, let's say d mu of phi squared is just d mu phi d mu phi plus phi d mu phi product rule. And they enter with plus signs, and it's precisely these plus signs that will cancel out those minus signs, and so I expect that improved version then, let's say d mu tilde, let's find the canonical d mu plus this improved d mu. Okay. All right, very good. Now we've learned that the Wilson-Fisher theory is in fact a classical only invariant theory. The canonical energy momentum tensor generated by the Newton's theorem is symmetric, actually, symmetric and conserved, but not trace-free, but we can always improve it by adding this improvement term, and the resulting improved energy momentum tensor. This guy is symmetric, conserved, trace. Okay.
Yes, sorry. I have a question. How would you want to find the improvement variable?
So at this point, I use some snarky answer, like years and years of experience. But actually, it's not so difficult to see these days because I know what I want to cancel. Right? So I know that I need to get a term that can generate these two terms here. Right? And I know that when I differentiate something like phi squared, then I generate factors of 2. And I know that something like this is going to contribute to these kind of terms. But it really is one of these things where, you know, if you work with derivatives enough, then you start to see the kind of pattern that you need for this. Okay. Very good. So let me finish this lecture by telling you what it is that we want from our energy momentum test. So properties that we require from as follows. First, we need energy and momentum to be conserved. So we want that T mu must be conserved. This would mean that the mu of T mu is vanished. T mu must be symmetric. This is because we want to couple this, whatever we're talking about, to gravity, for example, then it certainly must be symmetric. We phrased it another way in the last lecture. We said that if I had any transformation that was an isometry of the metric, then T mu was necessarily symmetric. Point number 3 is that I wanted to generate space-time transformations. Well, we know already about the generators for space-time transformations. These are the momentum generators and, for example, Lorentz generators, right? How does it gel with the idea that you must generate space-time transformations? Well, translations in space and time are generated by the operator P. But P is in fact nothing but the spatial integral of T mu naught. And then Lorentz transformations generated by operators that we will call M mu in the past. And these M mu's are again spatial integral of some new object that I'm going to call curly M. Curly M has three indices, two of which will be three indices mu and mu. The third I'll fix will be the time component, where this paragraphic M mu lambda is defined to be T mu x lambda minus T mu lambda. So from the energy momentum tensor, I can generate, I can define these Lorentz generators, both momentum space-time translation generators. Okay, so what you're going to show in the next tutorial is that these objects defined from the energy momentum tensor have been satisfy the same algebra, so the same algebra as the momentum generators and the Lorentz generators that we explored before. Okay, and if they satisfy the same algebra, then they're the same object as far as that is. Okay, so that's all that I have to say about this. Next time, up next week, right? I want to start by saying a little bit more about the energy momentum tensor. In particular, we are going to answer the following question. Are scale transformations, are all scale transformations necessary for formal functions? We're going to do that by exploring some properties of the energy momentum tensor. I'm going to show you that the answer is in 2 dimensions, yes. And in higher dimensions, it is still an open problem. So we don't actually know the answer to that. Okay. And we'll do that by studying the conformal one elements. Okay. Another